So, good evening, everyone. Welcome to a New England Zoom webinar session. Tonight's topic presented by Worcester Polytechnic Institute student team from High Power Rocketry Club. It is a multidisciplinary team of passionate students who aspire to be the next generation of space engineers and pioneers. The NASA-sponsored initiative involved in the hands-on project on designing, building, and launching a rocket to a target altitude in a controlled manner and deploying a payload during descent to about 500 to 1,000 feet above the ground. The payload is designed to part from the launch vehicle, autonomously land, self-level, and take a 360-degree panoramic photo of the landing site and transmit the photo to the team. See the impressive work of students who designed, build, and launch a sounding rocket that soars to the altitude of over 4,500 feet and execute this complex mission. So with that, I'll pass the rest of the presentation to Julia. Yeah.
Thank you. All right, I will. I do believe I need the screen sharing permissions. Thank you. Okay. All right, we'll get started. So thank you so much for that introduction. This is our AIAA New England presentation, and thank you very much for having us today. So as you mentioned a little bit about, we are, of course, a team of 40 to 50 students coming from various majors and backgrounds at Worcester Polytechnic Institute. Our members are divided into two team divisions, rocketry and payload. Each division has 4 to 5 subteams that focus on similar subsystems of each vehicle. This is our third year competing in the NASA rocketry competition, the University Student Launch Initiative. Fortunately, we did have to discontinue with the competition this year due to COVID-19 related setbacks, but nevertheless, we continue to pursue our project. We're happy to say that with the help of our sponsors and mentors, we've been able to continue this project on our own and are very excited to show you our progress and designs today.
So as Julia mentioned, due to the COVID-19 pandemic, our timeline looked a lot different than most years. Over the summer, some members of the team were placed in 3 to 4 person groups, which were tasked with designing their own rocket and payload. This was an effort to see if we can improve upon for next year's competition and to continue to come up with new ideas for the future. Once the USLIA handbook was released and we were back at school, we welcomed new members and started working on our proposal. In October, we were accepted into competition and begun to narrow down our designs for PDR. During this time, subscale rocket construction was taking place and with an anticipated launch date. Unfortunately, the night before our launch, our campus had a spike in COVID cases and our campus was partially closed. We were unable to launch our subscale, meet in person, and the team ultimately decided to end our journey with the competition due to this. Over the winter break, the team was still able to progress with building a payload prototype and testing every single component. The team now sets its own internal deadlines, with our first being the CDR. Instead of presenting to NASA, as we usually do, we presented to our sponsors and mentors instead, gaining valuable feedback. Right now, with campus recently open, we have been moving steadily forward with full-scale construction, and the next documentation will be the flight readiness review, and we are hopeful to launch by the end of this year. Although we are a competition team, there are many goals the team strives for every day. Mission design and execution not only pertains to the requirements set by the competition, but also internal design goals we set ourselves. Each year, the team chooses 1 or 2 new major tasks that they would like to add or improve upon to the rocket and or payload. It is not only important that these designs are well thought through, but well executed. This provides our members with the full engineering cycle experience, since they see the project from concept all the way through to fruition. Throughout this competition, there are several design reviews, which are most recent being CDR, or the Critical Design Review, being 336 pages long. As engineers, it is not only important to create, but also to be able to effectively describe the idea and document its journey. This extensive record of our project can be beneficial in many ways, namely for future members of the team. Education and engagement is crucial for our team's sustainment and also the community and members' benefits. The team participates in several outreach opportunities throughout the year to give back to the STEM community. This project is a place where students can put concepts they've been taught in class into practice in addition to learning hands-on. The team holds workshops and throughout the year ensures that new and returning members alike learn something new and improve on their technical and professional skills.
All right, so I'll be taking you guys through a little bit of an overview of the vehicle that we're launching. So this year's rocket is a little less than 10 feet tall, and it weighs nearly 50 pounds on the pad. It flies on an L-class solid rocket motor, with which we will reach an apogee of about 5,000 feet. We're flying a number of advanced systems on this vehicle, including our first fully custom integrated flight computer that performs data collection, telemetry, and GPS tracking, as well as does the control of our active air brake system, which we are going to use to target an apogee of about 4,550 feet. Recovery is handled by a pair of redundant altimeters that deploy a drogue parachute at apogee and a larger main parachute close to the ground. And the entire vehicle is highly modular with standardized airframe attachment hardware, removable fins, and electronics bays that are specifically designed for accessibility. This vehicle really is the culmination of the past 3 years of this club's existence, so we're very excited to tell you more about it. So we'll get a start with the aerostructures team. So the aerostructures team handles all of the external components of the launch vehicle, including the nose cone, the body, the fins, and the tail cone. So this year we're flying an entirely fiberglass airframe and nose cone with custom carbon fiber sandwich fins and a 3D printed tail cone. So the team started off focusing on airframe and nose cone selection. So these are commercial components, so it's important to find the right balance of cost, weight, and strength. In our case, we attach all of our internal airframe components using bolts rather than the more typical adhesive. So it's important to find an airframe that could withstand those concentrated loads in those bolt holes. In the end, we chose fiberglass, which won out for its high strength, radio transparency, as well as its dimensional stability. The design of the tail cone is critical to reducing the base drag of the vehicle by offering a smooth transition for the air flowing from along the body to returning back to free stream flow. So including the tail cone allows the rocket to fly a little bit higher than it would otherwise. We're using a 3D printed tail cone that can both reduce the drag and also serve as a shock absorber to protect the motor casing during landing. Some of the most critical components of the vehicle are the fins, which are required to maintain stability and are subject to a challenging aerodynamic environment. To keep the vehicle lightweight, we use a carbon fiber sandwich panel with a plywood core, which offers extremely high stiffness with a low weight. To ensure the fins would not encounter aerodynamic flutter during flight, we estimated their strength through classical laminate theory and were able to calculate the estimated fin flutter velocity. We've also just recently completed an analysis of different laminating epoxies, which we'll use for our fins. That will guide our choices for fin construction. And we have very recently manufactured our fin cores using the school's laser cutter. Up next for the aerostructures team is completing the composite layup for each fin, followed by a series of fin tests. So we plan to measure the bending of the fin in response to an applied load at the fin tip to characterize its stiffness. We also want to measure the twisting response of the fin by applying a known torque at the fin tip and measuring the angle to which it bends. This test will allow us to determine the effective shear modulus of the fin, which is the really critical number for our fin flutter calculations. So we'll use that data to confirm our estimations. The team will also be preparing the airframe for integration, which involves cutting the airframe sections to length and preparing each section with bolt and bend holes for component attachment.
Next up is an overview of the propulsion bay, which is located at the aft end of the rocket. The propulsion bay is composed of the fin can and the motor retention system. The fin can is designed with the intent to ensure that the fins remain secure throughout the flight of the rocket. The system consists of 4 fins, 2 centering rings, brackets to secure the fins, and brackets to secure the centering rings, as well as rail buttons and the tail cone. The motor retention system consists of the thrust plate, those same centering rings, and a motor tube. This system ensures that the motor is secured and centered within the propulsion bay. The thrust plate in particular helps distribute thrust from the motor to the airframe. Now taking a bit of a look at our completed work to date on the propulsion bay, in terms of simulation, we have conducted simulation using ANSYS software, especially a static structural analysis on the thrust plate and the radar bracket assembly. Locations of high displacement, von Mises stress, and minimum safety factor were solved for to verify the reliability of our thrust plate. Utilizing symmetry tools in ANSYS, as can be shown on the right side of the slide, we were able to analyze a quarter section of the thrust plate to reduce computing time and allow for greater mesh refinement. An adaptive convergence plot was created for the equivalent stress of the thrust plate to expose any possible singularities in our simulation, allowing us to run 5 iterations of mesh refinement. We found that the equivalent stress does rise after our first iteration and then flattens down, converges to about 19,000 PSI. The convergence plot verified to us that our calculated results are indeed mesh independent and no singularities exist in the model. Furthermore, we're moving on into manufacturing at the moment, and we have made significant progress on completing the CAM needed to machine certain components. And last week, we were able to machine a fixture plate for our thrust plate, and we actually just today finished manufacturing another fixture for another component. Looking a bit at our future plans for the propulsion bay, our subteam intends to complete all remaining CAM for the machine components in the fin can and motor retention system and finish machining any of the remaining components. In the photo shown on the slide, you can see our pallet fixture for the radio brackets on the mini mill. And in the second photo, you can see an example of the CAM we are creating in a program called Esprit for the radio brackets. Also in the following weeks, we aim to complete any fabrication using a mini mill and equipment in our school shop. And then we will move on to constructing the fin can and motor retention systems.
The mechanical systems team works on 2 major components of the vehicle: the air brake system and the avionics bay. The air brakes pictured on the left consist of 4 panels which extend out from the vehicle's airframe, causing an increase in drag on the vehicle by actively controlling how far the fins extend. We can vary the drag produced, and with a well-designed control law, we will be able to consistently reach our target apogee, accounting for variable factors such as launch rod angle, wind, vehicle mass, and motor performance. The panels are driven outward by a servo connected through a gear system to a cam slot plate. As this plate rotates through 90 degrees, the fins are extended along aluminum guide rails by roller pins that interface with the plate. This system allows for easy variation of actuation speed and torque without any of the moment arm concerns of a slider crank or similar mechanisms. The avionics bay consists of a central spine which provides mounting points for the air brakes, as well as the avionics computer and battery, and handles the load of the parachute deployment. The bay attaches to lower airframe using a twist lock mechanism, which makes installation and access at the launch site very easy. The entire system sits within the coupler tube between the lower and middle airframes of the vehicle. As seen on the previous slide, we have a complete design for the air brake system and the avionics bay, as well as a full CAD model for both sections. A key process we also completed was aerodynamic analysis of our rocket to determine if the air brakes would be effective and in order to simulate the flight. We used SolidWorks CFD to analyze the drag in our simulation to develop our control system, as well as on the vehicles during flight to determine how far to extend the air brakes. With data on the expected air brake force, we were also able to size our servo to expected loads. We define a kinematic model of the system and defined a minimum speed at which we expect the air brakes to operate. In our case, close to full extension in less than a quarter of a second. From this, we could determine an operating region of torque and RPM that the motor must be able to provide and choose our servo accordingly. We've also completed a prototype of our air brake system pictured in the bottom left of the screen. This prototype is made to test the functionality of our air brake actuation system before we cut the final plates out of fiberglass. From this prototype, we learned that we needed to adjust the fin rail slightly to allow for the fins to properly slide through the PTFE, and that we needed to modify the attachment points for the actuation gears in the gear system. In the coming weeks, we will be modifying our design to incorporate the necessary changes found during prototyping. Once these changes are made, we will start getting our structural and actuation plates water jet cut out of fiberglass along with the fins cut out of carbon fiber. We will also be machining the major components of the avionics bay and the FID guide rails out of aluminum, and all the plastic components will be 3D printed before assembly. Once manufacturing is complete, we will begin assembling both our air brake system and our avionics bay. We then plan to test the air brake system on the ground, loading the fins with weights to test the strength of the mechanism, as well as incorporating it with the avionics system to complete hardware in the loop testing.
Next, we will begin discussion of the avionics system. The avionics bay is located at the coupler between the middle and lower airframe sections and serves two critical functions for our rocket. The first is to use an array of onboard sensors to collect flight data and transmit live telemetry during flight. The second is being responsible for actuating the air brake system to help the vehicle achieve its target apogee. The final system will be controlled by the team's custom flight controller software, and all electronic components will be integrated into a custom printed circuit board of our own design. Moving to the next slide, we'd like to share with you our progress to date. The avionics system will be controlled by a Teensy 3.2 microcontroller, which will interface with a number of peripheral devices in order to meet the team's objectives. Several sensors will be used, including an accelerometer, gyroscope, magnetometer, and barometer to measure the vehicle's heading, altitude, and acceleration. A GPS is also included to track the rocket's position and velocity during flight. The rocket will provide live telemetry during flight, as all flight data will be transmitted to a ground station via radio transceivers. Additionally, flight data will be recorded to a serial flash memory chip on board the rocket for redundancy and for review after flight. The images in the upper right corner of the slide depict testing of the GPS. The final system will feature a single board solution for the electronics hardware, keeping it neat and compact while ensuring that all components are secure within the avionics bay. The team is in the process of designing a custom printed circuit board, which will integrate all of the electronic components. The PCB design work is being done in KiCad, and so far the schematics for the board have been completed, as shown in the lower right-hand corner.
As for the, could you go back one slide? That slide wasn't done yet. Sorry. Thank you. So as for the software that's running on the board, we've been developing that in collaboration with the electrical and programming team on Payload. That's being written in C++ to interface with all the peripherals using various serial protocols, specifically I2C and SPI. And that will also manage things like detecting what state the vehicle is in and how it should be reacting at each given time. So far, we've gotten most of the low-level interface code done, and it's going quite well. In order to test and develop a controller to control the air brake system, we developed a plugin for OpenRocket, the rocket simulator that we've been using to generate our mission performance predictions. And this allows us to simulate additional drag on the vehicle based off the simulations done by the mechanical sub-team on drag of the fins. With this, we've designed a simple and will hopefully be easy to implement PID controller to manage the projected apogee of the vehicle to ensure that it converges with the target apogee. You can move on to the next slide. Thank you. As far as future plans go, we plan on going and finishing up our PCB layout so that we can actually have it manufactured and tested. This involves doing some routing and making sure that everything's all connected up and that we've designed something that's safe. Then it can then be sent out to a board manufacturer for manufacturing and SMT assembly. As far as software, we'll be continuing to do finalizing our code, writing more system state management, as well as hopefully doing some hardware in the loop testing once we have the actual hardware. Lastly, once all that's done, we'll be implementing the control law designed in simulation onto the actual board so that it can be tested with the full board and the full air brake system.
The purpose of the recovery system is to safely land the rocket within certain descent time, drift distance, and impact velocity parameters. Our recovery system is a two-stage system with a drogue parachute released at apogee to stabilize the descent of the vehicle and a main parachute released at 600 feet to reduce the descent time for a safe touchdown. This dual deployment system greatly reduces descent time and thus drift distance over a system which deploys the main parachute at apogee and reduces shock loading when the main parachute deploys over a system with no drogue parachute. Recovery events are controlled by two redundant altimeters, which ignite black powder charges that separate the airframe and release the parachutes. All the recovery electronics are housed in the recovery bay between the middle and upper airframes. This bay also connects the upper and lower sections of the vehicle through nylon shock cord attached to each section. The design of this system began with the structural design of the recovery bay, which consists of a central aluminum spine with adapters to U-bolts on each side, which will connect to the parachute hardware. To ensure the spine and adapters would handle the expected loads, we ran FEA simulations on the main components with expected parachute deployment shock loads. We calculated these loads by conducting a numerical simulation, estimating the parachute opening time and inflation area using standard methods. We designed and 3D printed an electronic sled that fit around the central spine and holds the altimeters, batteries, and arming switches. By using two altimeters, we reduce the chances of recovery failure, which is one of the most common causes of rocket failure. Adding to our redundancy is the use of altimeters that detect apogee by different methods. Our primary altimeter detects apogee based on barometric pressure sensors, while our backup altimeter uses an inertial measurement unit. These systems have recently been assembled onto the sled, and tests on the altimeters are ongoing.
The next steps for the recovery system are to complete recovery bay assembly and to finish wiring and testing the redundant altimeters and arming switches. Once the recovery bay is fully assembled, we can proceed with larger scale testing. This includes pad endurance testing, where we ensure our recovery system can still function after an extended period of time in the armed configuration, and the critical ejection testing, which informs us how much black powder we will need to successfully separate the vehicle sections in flight.
On this slide, we have the payload overview. The task of this payload is to autonomously land, self-right, orient within 5 degrees of level, and capture a 360-degree panoramic photo to transmit to a ground station. In order to complete this mission, we split the payload into 4 subsystems: retention, self-righting, stabilization, and electronics/programming. Each sub-team of payload is responsible for one of these subsystems. Our payload is approximately 5.95 inches in diameter by 8.61 inches long and weighs roughly 5.68 pounds. On the slide, we can see the payload in 3 of its phases: the landing phase, the self-righting phase with its pedals fully extended, and the stabilization phase with its legs fully extended.
Here we begin the recovery overview. The payload retention system is designed to safely retain the payload during flight, separation, and landing operations. The system consists of 4 separate mechanisms: the alignment pins, the tender descender, the chute release mechanisms, and the rotary latch mechanism. The payload is axially and rotationally retained during flight through 4 alignment pins located in the upper airframe that slot into the payload's top section. When the airframe separates to deploy the drogue, the payload is also pulled out of the upper airframe. The payload is retained to the rocket after drogue deployment via the tender descender The tender descender allows the payload to remain outside the rocket's airframe where it can be released at the desired altitude. The tender descender assembly is how we detach the payload from the rocket during descent. This subassembly consists of the tender descender and an altimeter to trigger the mechanism. At 1,000 feet AGL, the altimeter triggers the tender descender to separate, thus releasing two metal quick links as shown. This allows for the shock cord of the payload to detach from the shock cord of the rocket. The payload descends until two redundant Jolly Logic chute releases allow the parachute to deploy at 850 AGL. The parachute controls the descent of the payload till landing. Upon detection of landing, the payload's electronics trigger a rotary latch to actuate, releasing the shock cord that tethers the parachute to the payload. With the parachute detached, the parachute is free to deflate away from the payload vehicle, reducing the chance of entanglement. Our work has been testing individual electronic components of the retention system and optimizing the design to improve the overall form factor of each component. We have just completed the final assembly of the top section of the payload, housing the retention section. The chute release mechanisms are off-the-shelf rocketry items. The alignment pins are installed during airframe construction. The final tender descender assembly will begin once there is availability of our Nylon X 3D printer.
This section presents an overview of the payload self-righting system. The goal of this system is to bring the payload to an upright position after descent and landing. We decided to do this with three arms about the base of the payload, which we refer to as pedals due to the way that they deploy. Each is 6 inches in length, making up about 3/4 of the total payload's height, and has a slight curve about its width so that it better fits inside the payload's retention. We chose to have three pedals over a larger number to allow space for independent drive systems and other payload subsystems. We also wanted each pedal to be capable of righting the payload completely by itself. So by estimating the payload's final mass to be around 5 pounds, and assuming that it acts about the pivot point on the mount, we estimated the required torque to right the payload to be at least 30 inch-pounds. Each motor has a 499:1 gear ratio, which allows each individual pedal to produce approximately 84 inch-pounds of torque, which is more than enough to right the payload on its own. The motors are set at a slight angle towards the center of the payload in order to avoid exceeding its outer perimeter, and a limit switch and potentiometer are included to sense the position of the pedals before and during deployment. The mounts, gears, and pedals are all printed out of Nylon X. We decided to print as many parts as we could for ease of manufacturing and simplification of the assembly. We chose Nylon X due to its relatively high tensile strength when compared to other nylon materials, which made it optimal for use in manufacturing parts which we expect to experience a constant source of stress, such as the pedal arms and the gears of the drive system during deployment. Each pedal arm is 3D printed as one body with the output gear of the drive system and the input gear of the potentiometer included. This was done to further simplify assembly and manufacturing, allowing us to avoid the process of cutting metal gears and attaching them to the pedal and hinge pin. On this slide, it shows a prototype of the self-righting system. The prototype had a few changes to it to allow for ease of manufacturing. PLA was used instead of Nylon X for the printed parts, and plywood was used instead of carbon for the base plate. Also, a shoulder bolt was used instead of a machine shaft for the hinge pin. At first, the motors could drive the pedals all the way out to the extended position, but could not retract them. We determined that this was due to a printing artifact left on the top of the pedal's bevel gear, where the printer would over-extrude there. We fixed this by extending the teeth of the gear up to the next part of the pedal, which would be the outer housing for the shaft. And with reprints, this allowed the pedals to fully extend and then retract. And on the right, there's a video. I'm not sure if it was working, but for the next steps for this system, we're beginning to print our parts with Nylon X, and we'll want to test the bevel gears for stripping when they're subjected to the motor torque, as it's a relatively high torque. We also want to test their ability to fully extend and retract the pedals. In addition to this, we've printed the entire pedal part and plan to print the base mount soon, and then machine the aluminum shaft so that we can begin assembling the entire system for further testing.
The stabilization system's objectives are to bring the payload body to within 5 degrees of vertical and to provide a stable and elevated platform for the payload camera to take a panoramic picture. The system, one of which can be seen in full on the left, achieves these objectives by using 3 modules evenly distributed around the payload's vertical center line. Each module consists of a sensor-controlled 4-bar linkage and a compliant foot mechanism. The modules are mostly made of 3D printed PLA and nylon X filaments, although some parts will be machined out of 6061 T6 aluminum. Each module uses a parallel 4-bar linkage that's designed to support the entire payload's weight, with a factor of safety of around 1 3/4. A payload 4-bar linkage was chosen over, for example, a vertical linear actuator due to its reliability, simple motion profile, and its familiarity to members of this team. The linkage is driven by a high torque servo through a 1-to-2 power transmission, which you can see in the middle picture. A limit switch and a potentiometer will work with the motor and payload electronics to track the position of the linkage and control each individual module. The gears will be manufactured out of aluminum using electrical discharge machining in WPI's machine shops. Finally, the system interfaces with the ground using a friction pad, which consists of a flexible polycarbonate plate, 2 layers of cross-linked polyethylene foam, 1 layer of polyurethane foam, and a custom tread 3D printed out of Cheetahflex compliant filament. The section view of this assembly can be found on the right. This foot assembly is folded into a U shape during launch, flight, and landing, and unfolds itself upon deployment due to its elastic nature. When in contact with the ground, the foot deforms and conforms to the terrain, which improves traction when coupled with the Cheetahflex tread. So far, a variety of simulations have been run on parts of the stabilization system. The first of these can be seen on the right, which is the output of a SolidWorks motion study. This study was used to find the maximum torque position of the 4-bar linkage, which was roughly horizontal. Finite element analyses were also run on the aluminum parts in SolidWorks, which allows us to find the areas of maximum stress and account for them. And actually, this slide has an animation. Julia, could you play that real quick? One more. There we go. Oops. There we go. All right. Finite element analyses were also run on the aluminum parts in SolidWorks, which allowed us to find the areas of maximum stress and account for them. All studies were H-adaptive, changing the fineness of the model mesh with a goal state of 98% simulation accuracy within 4 runs. In the case of the input crank pictured here, the study converged in 3 runs, producing the stress map on the right. This map was then used to find the factor of safety of the parts under their loading conditions. Some prototyping was also done, as can be seen on the left. 3 prototypes of the stabilization system were made out of PLA, which were then used to check the design itself and to test the stabilization code. Although the prototype mechanism was imprecise in its movements and the gear servo mounting was sloppy, these problems stem from the imprecision of 3D printing rather than issues with the design itself. Since most of the mechanism's parts will be aluminum since some of the relevant parts of the mechanism will be aluminum on the actual payload, we can use more precise manufacturing methods to create well-fit parts that will eliminate most of these problems. Finally, qualitative testing was performed on different foam composites. So a variety of these different composites were tested for the best balance between compressive resistance, flexibility, and ground conformity. So of the 16 composites tested, again, cross-linked polyethylene outer layers and a polyurethane inner layer worked best for our purposes. Since qualitative testing will be performed, the exact dimensions and material properties that the composite requires are currently unknown. Next steps for the subsystem include manufacturing, assembly, and testing, not necessarily in that order. Currently, we have successfully printed all PLA parts, and we're working to get the aluminum and nylon X parts finished as soon as we can. Once all the parts have been manufactured, we'll begin testing individual components, mainly the system's sensors, the foam composite, and possibly some 3D printed parts. After the specified components have been tested, a single stabilization module will be assembled and tested on its own. And once the individual assembly has been tested, 3 modules will be integrated into the payload, and the whole system will be tested.
All right, we'll now begin an overview of the payload electrical system. The electrical and software subsystem is responsible for controlling all the actuated mechanical parts of the payload, which were just previously described. We use geared DC motors primarily and their respective controllers with feedback from rotary encoders and limit switches in order to properly actuate these mechanisms. Our firmware, as you can see, was designed as a state machine in order to achieve the desired functionality and organization of our code. Because all lander operation must be fully autonomous, any action required at a given moment is mainly a function of current and previous sensor measurements. So state machines help to ensure that no matter what readings are observed, a robot will always behave in a consistent and safe manner. As just mentioned, the lander will transition states when certain events occur, which is based on data sampled from sensors that we have on board, such as a barometer and an inertial measurement. Finally, for safety, we're also going to be using different guard conditions and timeouts just to ensure that the states will transition properly should anything go wrong during flight.
The photography subsystem captures the panoramic photo and sends it back to the ground station. It consists of a 360-degree camera and a Raspberry Pi Zero. The PiCam 360 is able to capture 360 degrees horizontally and 235 degrees vertically with a single image. The camera is housed at the top of the payload, and the diagram above shows the camera's field of vision. The camera's mounting location and surrounding components are all designed to eliminate obstruction and distortion to the image taken, and the surrounding components are a matte black color to avoid reflection and glare into the lens. The original idea was to use multiple cameras that could cover 120 degrees and stitch the picture together. The camera's rotation and stitching of the images was a significant factor in ultimately choosing the PiCam 360, as it doesn't require rotation or image stitching. The Raspberry Pi was chosen for its lightweight and cost effectiveness, and it is used for controlling the camera as well as storing the image and processing. The picture on the right is an example of a photo taken during the testing of the camera and the Raspberry Pi. Currently, the top part of the payload is in the process of being built.
To develop and prototype the overall electrical subsystem, we started out by researching components based on the desired specifications. Our original design used an Arduino Nano for our main processor, but we ended up switching to a TNC 3.2 since it's faster and so we could develop alongside the avionics team who also uses a TNC. Since the winter, we've been writing and testing code for each individual sensor in order to integrate them into subsystems and the state machine. We remotely developed code for the TNC 3.2 and the Raspberry Pi for the photography system by cross-compiling it to a hosted server as shown in the picture on the right. We're currently finishing testing motor controller functionality with encoder feedback to implement PID control in our state loops, which is pictured on the left. Once all software and components are tested on breadboards, like the pictured setup, we will move to designing and assembling a PCB, like the avionics team, to reduce the size and number of connections on the final lander model.
Lastly, now with the conclusion of our technical design, I'd like to give a brief overview of our team's safety practices. Safety is the highest priority of WPI HPRC and plays a central role in all team activities and decision-making. The club has a designated safety officer who is responsible for educating team members about safety and ensuring all safety guidelines are met. In order to promote a culture of safety for all members, team members must agree to a safety contract and attend a mandatory safety briefing. The team operates in full compliance with all NAR and FAA regulations. Our team maintains detailed hazard analysis tables in order to identify any and all potential risks to the successful completion of our project. Each of the hazards identified are categorized by probability and severity, as shown in the risk assessment matrix displayed on the bottom of the slide. These hazards have been further classified according to a color code system to assess risks and take appropriate mitigation protocols. To ensure that everything runs smoothly on launch day and that all safety procedures are followed, the team has compiled several checklists for guidance. An example of this is in the upper right of the slide. These checklists serve to guide the team through final assembly and launch procedures, taking care to break down the process into easy-to-follow steps. Safety checklists are followed carefully at all launch events to ensure that all steps are completed in compliance with safety guidelines.
We'd also like to give a special thanks to our sponsors, particularly WPI Tinkerbox, eBAD, and Test Devices and Consulting Structural Engineer. Without the support of our sponsors and mentors, we would not be able to enjoy the activities that we participate in through HPRC and be able to construct both our rocket and payload. Now that we've concluded our presentation, we're happy to take any questions. So thank you again for allowing us the opportunity to present.
Okay, thank you guys. Excellent presentation. So there's 3 questions from Tom. Tom, would you like to read them up? I'll allow you to talk, I think.
Let's see, I don't have it in front of me, but the first one, yes, right. Yeah, you got a solid propellant system. So what was your mix of solid propellant and how did you form it? How did you test your formation?
Yes, I can take this one. We use a commercial solid rocket motor. So it's manufactured by a company called Cesaroni Technologies Incorporated. So they use a standard ammonium perchlorate composite propellant in their mixture. The idea of building and manufacturing our own solid fuel motors is certainly very enticing, but we've had some issues with getting the school to sign off on it. So not this year, but certainly maybe we could have an answer for that in the future.
All right, good.
I think additionally, that's also against the rules of the competition that we're currently in. Or I guess we're not in anymore, but not NASA student launch.
Right. I guess I'm used to the years ago, part of the rocket clubs. One of the biggest things was making the propellant, whether it was solid propellant or liquid propellant. Okay, thank you. Let's see. Oh, the other question. So are you doing wind tunnel testing? Take your assembly and check to see that the drag fins are working well, your controls like that, and under various wind conditions, and also to make sure you're not exciting any modes in the rocket when you deploy your fins and drag fins?
Yeah, for sure. So this year, WPI doesn't actually have any wind tunnels large enough to test our entire rocket assembly. We had some plans in the works from previous years to test them in some of the smaller test subscale models in the smaller wind tunnels. But unfortunately, we can't have access to those this year just because of all the COVID regulations. So.
Got it. And I'm not sure if the Wright Brothers tunnel is reopened yet at MIT. It's probably the same thing because that should be big enough to test it in. But probably again, the pandemic would cause some problems. And my last question was, maybe I missed something, but you got a payload that's got to come down and land, and you've got the parts of the rocket coming down. So I'm assuming you have 2 parachutes and you separate in air, and then the payload lands separate from the others. And so how do you deconflict? And if you only have 1 parachute, how do you keep the whole assembly from being dragged away in the wind?
Yeah, so pretty much what happens is we have our drogue at apogee, and then we actually detach our payload from the system with the tender descender. If Julia wants to go back to slide 23, we can see the wiring diagram. So pretty much what happens is that we adjust the drogue route, and then we're able to separate the payload from the airframe sections. Right. And then the payload falls an additional 150 feet to 850 feet, where it then releases its parachute. So we have that gap in altitude where the two can separate, the 2 bodies can separate. And then our parachute on our payload deploys, and then our rocket continues to descend till 600 feet, where it actually begins. Sorry, no, the slide before that one, Julia. I don't know why they're both labeled 23 on my end. Oh yeah, so 22 now. So see those 2 rings on the tender descender? That's where it separates at that block. And then the parachute on the payload, we've also chosen such that it is it will tend to land more directly downwards. We chose a polyconical parachute for that. And the parachute on the payload is basically then designed to just land and fly away. The rocket itself deploying after the payload is detached and at a lower altitude will actually separate the two when they land on the ground.
Okay. Oh, one last question, and thank you for your answer there. Everything, of course, is above a ground level, and you're measuring inertial coordinates, and you're also measuring barometric. So at some point, do you have to put in the ground altitude into your computer before you launch, so that if you're launching at White Sands at 4,000 feet, or you're launching at some other place at 6,000 feet, you don't crash because the whole thing has the wrong data?
Exactly. So one of the things we can do is there is a calibration in the altimeters. I believe off the top of my head that the actual barometer of our primary altimeter only requires a recalibration after some change in altitude. And I think if we, I'm pretty sure we like zero it out at the actual field. Some of the older members who have experience with the altimeter might be able to correct me.
So for the just commercial altimeters you're talking about, right? Yeah, those, as soon as they're initialized, they zero themselves out. There's no manual zeroing process that we do. And that's just part of their design, such that they're as simple as possible to use for average rocketry people.
Oh, that's good. Okay, I just all the little things that clicked in the back of my mind is where something could go wrong. Thank you. Done an excellent job.
Okay, so next question is a Christian North. Yeah, go ahead, Christian.
Hey guys, great presentation. Just give me 1 second. I heard that you guys use all Imperial in everything. If I tell you have to do this presentation in Europe tomorrow, do you have all the same data in SI system, in metric system?
I can't confirm if we have all of the data in SI, the metric system, but I know we have chosen to do Imperial throughout this whole year because NASA requires it, and that's the competition that we usually follow. Aside from that, I feel like we would be using metric if we weren't in that competition.
Okay. Thank you for that.
Okay, next question is Charlie. Charlie, can you unmute yourself?
I'm trying.
Yeah, okay.
Okay.
There you go.
I'm looking at the shot cord diagram, and I think this came up a minute ago from Tom, but when the drogue's out, the middle and lower airframe is going to be hanging straight down below the upper airframe. And the tender and descender have to not be entangled in that cord coming down. Isn't that true?
Yeah, so the way we ensure separation is we make sure that basically what we do is we lay out the entire vehicle with all the shock cord, and we make sure that like if we anchor it at any point, we can swing all the components and not have them hit any other components. So the general rule of thumb for that is about 3 to 4 times the body length of the vehicle in shock cord between sections. So that is usually enough to keep anything from being tangled, and we haven't had any tangling issues when we've used that in the past.
All right, so the shot cord diagram, you could change that, I guess. All right, so the next thing is, how do you ensure acceptable tip over during ascent? I mean, they're not spin stabilized. I would have heard that. And things don't fly straight. How do you account for that?
Yeah, sure. So we are not spin stabilized. We ensure that the rocket flies where we want it to go by tilting the launch rod. So it depends on the wind conditions on the day, but we'll generally tilt it between 85 and 80 and 85 degrees from horizontal. So that'll kind of make sure that the rocket flies in the direction we want to go. As far as the stability of the rocket, We calculate the center of pressure using of the vehicle using a program called OpenRocket, which is just a general purpose simulation tool for high power rockets like this. And what we make sure is that the rule of thumb for that is that our stability margin, or the distance between the center of gravity and the center of pressure, is at least or around 3 times the body diameter. So with that, the vehicle is statically stable, and when we fly it, won't flip out of control or anything like that. So in addition to like the static stability criteria, OpenRocket also does like a full 6 degree of freedom flight simulation. So we can make sure there aren't any issues with like roll pitch coupling or anything like that, any of the dynamic modes that might also cause our vehicle to go unstable.
What about the center of gravity? Because you got parachutes, everything else is solid. So you have to estimate where that center of gravity will be on the flexible parts, or you got a lot of cords too. Yeah.
Yeah, so the parachutes themselves are very well packed within the vehicle. So not exactly like your Apollo, where I think they said the parachutes were like the density of oak, but they don't move around that much during launch. For the weight of the rest of the vehicle, we have weights for like the airframe and the other major components like that from the manufacturer. And then we use SolidWorks to estimate the weight of all the other components that we're making ourselves. So from that, we're able to get an estimate of where the center of gravity is. And then once we have the vehicle, we can weigh each of the components and adjust our estimations to determine the actual center of gravity.
Good. Okay. Will the aero environment affect the barometric altitude determination?
Can you be a little bit more specific on that?
A barometer will tell you what the altitude is if you set it.
Oh, yeah. Okay. Yeah, I get what
you got a lot of airflow. Yeah.
Yes. So as far as like the effects of temperature and humidity or anything like that, the altimeters just implement like your standard international standard atmosphere model. So it's certainly an estimation of the actual altitude reached. That it can vary if it's like really cold on the ground or anything, but in the altitudes that we reach, the temperatures tends to even out across seasons. So it's a pretty good estimation just from the pressure. As far as actually measuring it on the vehicle, we are careful to drill vent holes in the airframe so that the internal compartments that have the altimeters in them will reach the same pressure, and we drill them on 4 sides of the vehicle so that even if we're flying at some angle of attack, we don't get any unwanted like additional pressure or decreased pressure within the vehicle.
What do you go ahead?
If I can add as well, we do have 2 altimeters, one that is barometric based and one that is accelerometer based. So if there happens to be any issue with the holes we drill in, the accelerometer, which is the rating 4, could deploy as a redundant system.
All right, that was my next question. If the 2 altitude measurements disagree, which do you use?
So for the competition, if we're still doing it, we would use our primary altimeter, which is the barometric altimeter. As far as our own estimation, I think we'll probably stick with that. The altimeters do not actually communicate during flight. So even if they disagree a little bit, there's no real issue with that.
What's the max speed you're going to achieve?
It's 619 feet per second, which is something like 0.5 Mach or a little bit above.
Yeah. So, all right. So you couldn't test that on a anything except a rocket, I guess, to see if the atmospheric pressure affects the barometer. But I'm asking questions that must have been answered years and years ago. Let's see, where will competition take place?
The competition typically takes place in Huntsville, Alabama at the NASA Center and also at Redstone Arsenal. That typically takes place in person. They weren't able to do that last year. So this year they're offering more of a hybrid because they don't know if they're still putting it on in physical space that year, this year, but teams are allowed to compete virtually and send a video of their launch and all the flight data of their competition launch.
Oh, this has really been a marvelous presentation. I'm really excited about it. Here I'm done.
Okay, thanks, Charlie. Helen, your turn.
Hello, great presentation, really enjoyed it, very clear presentation. So my question was, what sort of information do you have about the landing site that will inform how you deal with the stabilizers?
Yeah, I can handle that one. So our landing fields are kind of the one thing that stays very constant between years. We have two main test sites we go to, which is one on Lake Winnipesaukee, the other one up in Vermont. Either we're going to end up with a roughly or a tilled or kind of flat dirt surface. But depends between year to year, depending on the actual surface roughness between the two environments, or we'll end up on an ice environment with snow. So either of those two choices help inform our design for our compressiveness and tread situations. And the important part of why we chose to go with a more modular foot design was so that we could account for the varying environments between the two.
Thank you.
Okay, so last two questions from Daniel Peters.
I'm going to unmute. This is a question for Bridget, I believe. I was interested in the parachute design. I've never done any myself. What simulation design tool or simulation design tools did you find most useful?
Thank you for your question. So pretty much we used a book called The Parachute Recovery System Design Manual by T.S. Nake, and then we used the opening times that we got from that book and the parachute area as a function of time to run a couple numerical simulations through MATLAB to determine the acceleration of the vehicle to ensure a safe descent and landing velocity.
Great, and that was parachute recovery design?
It was a Parachute Recovery System Design Manual.
Oh, great, that's perfectly right on the nose. And then the second question was just for Abby, I believe. Were there any encoders in the hardware pictures shown today? And if so, where do you plan to mount the encoders if they're not shown?
Right, yeah, thanks for your question. Each pedal, each of the three pedals for the subsystem has a potentiometer on the motor, and they're not pictured in the presentation, but they are in our CDR if you would like a copy of that.
Yeah, I mean, we can try and point it out on the slides for you, actually. If you want to go hop to slide 25. At least on the self-riding arm, we have one that's it's a gear ratio off of the main pedal.
So it's a gear-driven potentiometer is what you're using as an
Yeah,
encoder?
there is a reduction between the pedal and the potentiometer. It's mainly for spacing. You can see in blue in the close view image, that's where one potentiometer is located. And then I don't know if we have a good picture of the one on the stabilization arm. We don't, but the potentiometer in there is located on the crank drive shaft. So it directly reads the rotational position of the crank.
Okay. The motors, these are I guess open loop motors. They just turn in a particular direction based on their brushes. They're brushed motors, so they just turn in whichever direction the voltage is applied. Is that the system?
the self-riding DC motors are, the stabilization system actually uses a continuous rotation servo.
Excellent. Great. You guys have quite the eclectic mix of designing and talent problems to solve. And that's, I can understand why the team is so large. Quite a bit of a project. Good work.
Okay, thanks guys. Excellent job, WPI team, and thank you for the presentation. So with that, we'll conclude tonight's session, and everyone has a good evening.